Today we're talking about exploring inverses of functions. We've already talked about inverses of functions algebraically. Today we're going to talk about it graphically and talk about their domains and their ranges. So, an inverse function interchanges the input and output values of the original relation. The other day when we had a function and we found its inverse algebraically, the first thing that we did is replace f of x with y. Then we swapped the x's and y's and solved that equation for y. So, an inverse function interchanges the input and output values of the original relation. Well, this original relation is f of x equals 2x plus 1. When we're talking input and output values, what are we talking about? We're talking about the x's and the y's. The x's are my inputs because I pick an x and then I find the answer. I find the y. I pick another x and I find the y. So in this case, the input values are my x's, the output values are my y's. If you hear the words independent and dependent variables, what are we talking about? We're still talking about our x's and y's, but which one is my x and which one is my y? I have an independent and dependent variable. Which one depends on the other one? Well, think about it. The y depends on the x. Whatever my x is, I pick any x value I want, I plug it in, I find the y. So my y value depends on my x value. So the x values are my independent variables or my input values. My y values are my output values or my dependent variables. Now look what this says. An inverse function interchanges the input and output values of the original relation. So if you have a set of ordered pairs, to find the inverse, just swap the x's and y's. It's all you're doing. When we're talking domain and range, remember the domains are the x values. The domain is the x values of that function. The range is the y values of that function. So if I have an original relation and I find its inverse, notice what happens. From the original to the inverse relation, the domain becomes the range of the inverse, and the range becomes the domain becomes the range of the inverse, and the range becomes the domain of the inverse. So in a minute, you're going to graph a function and its inverse, and if you'll notice, the domains and the domain and the ranges are going to swap in each of those functions. Now, the next sentence says, a relation is a function if for every element in the domain, there's exactly one element in the range. Don't let that freak you out. All that's talking about is if I have a graph, is this graph right here a function? It is not a function because, if you'll notice, this ordered pair, negative 1, 2. So a relation is a function if for every element in the domain, so negative 1 is in the domain, there's exactly one element in the range. So in this case, my domain, I've got a negative 1. The range, I have a 2. Well, for this ordered pair, that ordered pair is negative 1, negative 1. Well, I have a negative 1 in the domain, but it's also paired to a negative 1 in the range. So in this case, this element in the domain goes to two different elements in the range. So this is not a function. If you have a set of ordered pairs, those x values cannot be the same or you don't have a function. If you have a graph, if you'll notice, this does not pass the vertical line test. Remember, we've talked about the vertical line test. If you run a vertical line across your graph and your vertical line touches any 2 points on that graph at the same time, then that graph is not a function. That graph is not a function. It does not pass the vertical line test. So a relation is a function if for every element in the domain, there's exactly one element in the range. So if you have a set of ordered pairs, the x values cannot repeat. See, these x values repeat, therefore you don't have a function. The reason that's not a function with those ordered pairs, those x values repeating, if you plot those points are in a line vertically, and it does not pass the vertical line test. So, this says, remember from yesterday? Well, we didn't talk about this yesterday, but you know if a relation passes a vertical line test, then that relation is a function. We just talked about that. Now, here's a new test. We've never talked about this before. If a function passes the horizontal line test, so you know a vertical line test is with your line straight up and down. Well, the horizontal line test is turn your line horizontal. If it passes the horizontal line test, which means my graph cannot touch this horizontal line in two places at a time. So if a function passes the horizontal line test, then that means the inverse of that function is also a function. This is a special function, okay? So if a function's inverse is also a function, then the function is called a one-to-one function. So if a function's inverse is also a function, then that function is called a one-to-one function. So if a function passes the horizontal line test, it is a one-to-one function. What that means is when you draw its inverse, that graph will also be a function. Okay, so let's look at some examples. Example 1a here, it says use the horizontal line test to determine whether the graph's function is one-to-one. Well, notice this graph is a cubic function. It does pass the vertical line test, so it is a function. B is a quadratic function. It passes the vertical line test. It's a function. The third one is a linear function. It also passes the vertical line test. So it says use the horizontal line test to determine whether the graphed function is one-to-one. I'm going to turn my pencil horizontal. If you'll notice, my graph touches my horizontal line in one place at one time. So this passes horizontal line test. Remember, a cubic function, some of you are thinking this may be constant right across here. Pick you some x values. If you pick 0, remember this is a cubic function, f of x equals x cubed. Now it's shifted down 2, but I'm just going to use the function x cubed to show you that it is a function. If I plug -1/2 in the place of x, and I cube it, that's -1/8. -1/2 times -1/2 times -1/2 is -1/8. That's right here. Then I'm going to plug 0 in and cube it. 0 cubed is 0. So it looks like it's straight across, but when x is 0, y is 0. When x is down -1/2, the y value is -1/8. So those y values are not the same. If they were constant, then all those y values right there would be the same thing. Same thing with you plugging in a +1/2 and cubing that. You get a +1/8. They're ever so slightly changing, but they are changing. Okay, so a cubic function is not constant in that curvy part. Remember that curvy part ever so slightly increases. So this cubic equation, this cubic function is a one-to-one function because it passes the horizontal line test. That means when I graph the inverse of this function, then it will also be a function. In part 2, you're going to talk about drawing the graph. Example 1b, is this parabola a one-to-one function? No, it is not, because if you take any of these horizontal lines that are sitting here, your graph touches the horizontal line in both of these places. So that fails the horizontal line test. That means if I take and graph this function's inverse, and I'm just going to go ahead and show you what it looks like, it'll be a sideways parabola. And I'm sketching, so my points are not exact. But this is what the inverse of that parabola is going to look like, and you're going to end up and graph it right down here in this problem. But you can tell if you take, here's the inverse of this parabola. It does not pass vertical line test. Okay, that's because this parabola does not pass the horizontal line test. See, when you invert that parabola and turn it sideways, that sideways graph does not pass the vertical line test. So a parabola is not a one-to-one function. C part, you have a linear function. A linear function does pass the horizontal line test. So when you invert this line, and you will be graphing some linear functions on the example 3, then most lines are always going to be one-to-one. Can you think of any cases where a line will not be a one-to-one function? See if you can think about it. See if you can come up with a linear function that would not be a one-to-one function. What would fail horizontal line test? If you had a constant function, if you had the equation f of x equals -6, f of x equals -6, any constant function would fail the horizontal line test. All these y values are -6. Well, if you swap those x's and y's, guess what you're going to get? You're going to get a vertical line graphed at x equals -6. All those y values of -6 become x values of -6. They're in a line vertically, and that does not pass vertical line test. So that's talking about the horizontal line test and whether a function is 1-to-1. The second video talks about this example here.